WAS welcomes Montana Williams, a fifth-year PhD student at New Mexico Tech in Socorro, New Mexico, the same hometown to the Array Operations Center for the National Radio Astronomy Observatory's Very Large Array. Most of her time is dedicated to imaging non-thermal emission from classical novae using the Very Long Baseline Array, or as she likes to say, looking at cute star explosions. She's also a tour guide at the VLA, where she facilitates public tours so everyone can enjoy radio astronomy and the cute antennas. Please welcome Montana Williams.
Thank you. I take it that means we're ready to begin?
Yep, go for it.
Sweet, awesome. Just want to make sure. So yeah, thank you for joining me today for the VLA virtual tour. Before we actually talk about the VLA, and if my mouse works, which it seems to now be working, I want to tell you about the National Radio Astronomy Observatory, or NRAO as I'll call it. So NRAO actually got its start in 1956 on the East Coast in Green Bank, West Virginia, and Charlottesville, Virginia. And it was founded to enable forefront research at radio wavelengths and to provide world-leading telescopes and instrumentation and expertise, train the next generation of scientists and engineers, and to promote astronomy to foster a more scientifically literate society. And so the NRAO actually operates three major observatories: the Very Large Array, or the VLA, which I'll mostly be talking about today, my personal favorite, the Very Long Baseline Array, or the VLBA, and the Atacama Large Millimeter Submillimeter Array, or ALMA. And this is all funded by the National Science Foundation. So if you're an American taxpayer, thank you for my job. I appreciate it greatly. And so the VLA is actually located in the plains of St. Augustine, New Mexico, which is about an hour west of New Mexico. Before I talk about that, I want to talk about some of the other observatories to kind of give you an all-encompassing picture of what NRAO does. Of course, my personal favorite, as I've said several times, is the Very Long Baseline Array, or the VLBA. So it spans the entire size of the United States, and it's actually a little bit newer than the VLA, starting in 1993. And so it's 10 antennas spread throughout the United States, all the way from Mauna Kea and Hawaii, St. Croix and the Virgin Islands. And so when we talk about these arrays, we combine the signal from the dishes to make a telescope the size of the largest separation between the dishes. So in the case of the VLBA, that's a 5,351 mile size telescope. And we use it to look at things like this X-ray binary SS433. And so what you can kind of see is it goes from like a sort of very diagonal into it kind of goes flat. And so what this is the X-ray binary. It has jets coming out of it, and it's actually the precession of the jets. And so the precession is like when you have the little spinning tops that kids play with, or when you spin a quarter and it starts spinning perfectly straight up, and then after a while it starts to wobble. That wobble is it precessing. And so in the case, and much more energetic, of this X-ray binary, it's sort of changing where the jets are shooting out. And then not only do we have the VLBA, we also have ALMA, which is located in the Atacama Desert in Chile. And this is actually 66 dishes, most of which are about 12 meters or 40 feet in diameter. A few of them are 7 meters or 23 feet in diameter. So they're about half the size of the VLA antennas. And what that is really good at, so it actually sees higher frequencies in the VLA. So the VLA sees 1 to 50 gigahertz. ALMA sees about 90 to 350 gigahertz. And so one of the things they're really known for is looking at what we call protoplanetary disks. So we think planets form from disks. So it's kind of like Saturn and its rings, but instead of Saturn being at the center of it, it's a baby star. And then so we think that these disks eventually sort of form and clump together to form planets such as gas giants or rocky planets. And so these are three different protoplanetary disks that almost imaged. But now about our personal favorite, or main topic of today, is the Very Large Array. So as I mentioned, it's located in the plains of St. Augustine, which is an hour west of Socorro, and here's Socorro. So the Array Operations Center is located in Socorro. It's where I'm based. And then why did we choose the middle of nowhere, New Mexico for the VLA? So we chose it actually because in about the late 1960s, they decided that they wanted to build an array of telescopes. They decided that they were going to go further west for it, for one of two reasons. So one, because they didn't want the East Coast hogging all of the cute radio telescopes. And then the other reason is the East Coast is very humid, whereas the New Mexico is very dry. And so we like to put the telescopes in places that we call high and dry. So the elevation at the site is about 7,000 feet. So of course, there's less atmosphere that we're looking through. So it makes our data calibration and imaging much easier. And so also to give you an idea, ALMA is located at about twice that, at about 16,000 feet above sea level. The other reason too is because middle of nowhere New Mexico is really great for not having any radio signals, or what we call radio frequency interference, or RFI. And so if you can see here, I don't know if the laser pointer will work, but you see this mountain, this string of mountains behind the array. That actually continues all around the plains of St. Augustine. So it actually like creates a sort of natural barrier against RFI from surrounding communities such as Socorro and Albuquerque. And so some other things that you see here is, of course, the cute antennas. There's actually 27 of them, I think, in this. I actually didn't count, but I believe there are 27. And then so NRAO actually operates on the square mile at the center of the array. And then we have a lot of different buildings. A lot of these buildings are what we call tech services. So it's a lot of the buildings for housing the technicians that actually work at the site. Because while NRAO employs a bunch of scientists and software developers and engineers and data analysts, we also employ a lot of technicians and engineers at the site. And actually the technicians are the ones that usually work Monday through Friday at the VLA. And so that includes things like electricians, our own cryogenics team, our own rail crew, because we have double railroad tracks throughout the entire site, which I'll talk more about in a bit, and all of that stuff. And that's all the buildings you kind of see at the center here. And then I don't know, but these little two antennas that aren't actually on the thing, I think this is actually some of the ALMA antennas, because when they were testing them, they put prototypes out at the VLA to sort of simulate what it would be like at the Atacama Desert. It's really cool. I just noticed. And so the two main buildings that are actually used well, all of them are used, but the two main important ones are the antenna barn and the control building. So the antenna barn was actually the antenna assembly building. So the antennas were manufactured in Texas and then shipped out to the plains. And then they were put together in the antenna assembly building. Since then, we sort of repurposed it as a sort of maintenance barn, and we call it the antenna barn. And so we have maintenance days about once a week or twice a week, where we do, like, we turn the whole array kind of off, or we're not really doing any science stuff. And we do sort of band-aid fixes on certain parts, like if we have to replace receivers or some of the electronics as part of recording the signal or things like that. But for anything like hugely mechanical, such as the altitude bearing or the I think it is the azimuth bearing, that has to wait for its turn in the antenna barn. And it can take anywhere from about 6 months to a year for the antenna to get its spot in the barn. And then we also have the control building, which is where, of course, the control room is, and that's where the operator controls the array and the individual telescopes. And the operator has a really jack of all trades kind of job, because they have to, one, we don't have phones at the site, so that way we don't swamp out any of our cute radio signals by these cell phones or anything. But we have radios that have a very narrow band frequency filter on them. And so we use that to communicate with the operator, because, like, for example, if the technicians are going to one of the antennas, they tell the operator, because otherwise it's hard to communicate with someone from across the site where you're at and all of that. So they're sort of like the person you check in with and check out with. They also keep an eye on all the antennas, how they're working, on how the signal is as it's coming out of the antennas, and then how the supercomputer's doing. Because when we make these images that I'll talk about later, we combine the signal from pairs of antennas. So it's like antenna 1 with antenna 2 with antenna 3 and so forth. So for 27 antennas, that's a total of 351 pairs. And that is combined with our supercomputer that's in the control building, called the correlator. And so those are probably the two most interesting buildings. And so the antennas themselves are absolutely adorable, in my opinion. And so so we actually have 28 antennas. 27 are in use and on the array at any given time, and then one is sort of as a backup, and we rotate that through as maintenance requires. And the 28 antennas we have at the site are the original 28 antennas. We've never lost an antenna, so they're going on about 45 years old, but they're looking great and they're still doing a lot of good stuff. And then each antenna weighs about 230 tons. Most of the support structure and everything is steel, and then the dish itself is aluminum. And then it's about 83 or 25 feet in diameter, or about the length of a school bus. And they're about 10 stories tall. And so the design of the antenna is similar to your Schmidt-Cassegrain. So we have the primary and the secondary. The secondary up here is actually got sort of a dent in one side, and it actually rotates. And it does that because it funnels all the light into these bongo drums at the center. And the bongo drum's technical term is the receiver or feed horn. And so that actually selects which frequency we're looking at. We have a total of 8 receivers spanning from 1 to 50 gigahertz. Another thing you may notice is there's these sort of French fry lamp things kind of looking at some of them. And those are actually infrared lamps, because sometimes the receivers sort of ice over, which messes with our signal. And so they're actually to keep them warm. And so another thing you may notice is, and as I've mentioned throughout this, is we actually have railroad tracks throughout the entire site. We have double railroad tracks, and so that's over 40 miles of track. And the reason we do is because we move them. We not only move them to the antenna barn for maintenance, but we also move them every 4 months as part of our configuration change, which I'll talk a little bit about in a minute. But first, these cute transporters. So these transporters, we only have 2 of them, and they're unlike anything in the world. They were custom made to carry the 230-ton antennas. And so we have a total of 72 parking stations throughout the site, or actually 74. But we do this for the configurations, and this moves them to each one. And so the transporters weigh about 190 tons. So with the 230-ton weight of the antenna, they move at a speed of about 2 miles per hour with an antenna. And then without the antenna, they move about 5 miles per hour. There's also some safety stuff that goes into it. So for example, if the speed while we're planning to move the antennas is over 20 miles per hour, we won't move them. And that's actually happening kind of recently, like as far as I think still this week, but definitely last week. We're having an unusually windy start or into winter. And so we've had to postpone the move from A to D configuration because of all the wind. But yeah. And so as I've mentioned, we have configurations. So the antennas are on this Y shape, but then we actually move them sort of in and out about every 4 months. So we have 4 different configurations. They're creatively called A, B, C, or D. And so A, we like to say, stands for a long way away, and is about 22 miles in diameter. B is about 7 miles in diameter. C is 2 miles in diameter. And D is, we like to call it darn close together, and is about 0.6 miles in diameter. And we move them in and out like this to sort of zoom in and zoom out, so to speak. And so to give you a better idea is here's the VLA configurations viewed from above. So the smallest one, of course, is this little one here, and that's about 0.6 miles, and then the largest is about 22 miles in diameter. And so an actual interesting fun fact is, so the north arm, of course, isn't directly on north. It's about 20 degrees offset, and the east and west arm aren't truly east or west. It's just what we call them. But the other thing, too, is the north arm is only 11 miles long. There's actually was some hazardous geological features up there to build over. I think it was like a ravine or something. And then the east and west arm are actually 13 miles long. And so, as I mentioned, we can use this to sort of zoom in and zoom out. We have this phrase in radio astronomy, small is big and big is small. So when we're in the largest configuration, we can see the small structure. And then when we're in the largest structure, we can see the smallest stuff. Or maybe I misspoke, I don't know. But I have, finally, my mouse worked again. So in the A configuration, or 22 miles, we have the configuration large, so we can see the small structure. And then as we go from B to C to D, and as we get smaller, we can see the larger structure. But if you notice in the D, we can't see that fine structure that we see in A. So this is why the VLA is really unique in the fact that we can configure it in these 4 different configurations. And we move these configurations every 4 months to sort of offset the seasonal pattern. So that way we're not always looking in the same area of sky during like I'm trying to think. So we have a very wet season here at the New Mexico desert where it's called monsoon season, where we get basically all of our year's rain. And we don't always want to be like an A configuration during the monsoon season because then we can't do high frequency observations. And so that's why we do it about every 4 months. And so for this object, this is Hercules A. It's a radio galaxy. It's called a radio galaxy because it's really bright in the radio. And so what we can do for this one is we can actually compile or composite all 4 of these together and maybe even throw in some optical to get this cute picture. And so everything you see in the red and pink is hydrogen gas. And then everything else is the optical, and this here at the center is a dwarf galaxy. You know, there's a supermassive black hole. I can't remember how large it is, but it's huge. And then as things are sort of orbiting around the black hole, it can, of course, fall into the black hole because of conservation of angular momentum, and sometimes it shoots back out. And that's exactly what's going on here. When it was shot out, it was at relativistic speeds, but by now it's sort of not as energetic, so we don't see it anywhere else on the electromagnetic spectrum. And these jets are about 1.5 million light years wide. And then it's about 2.1 billion light years away. And so now I'm going to take a break to answer any questions about the antennas. I'll talk a lot more about the science after this, but I wanted to give everyone a chance to ask any questions about the antennas, the site, or anything like that, and to give myself a chance to drink some water.
All right. I'll start off with a softball question. Given that this is radio frequencies, do the antennas work as well in the daytime, or do you get interference from the sun?
So there is some interference from the sun, but so stars are actually tend to be radio quiet. Ours is only loud because we're right next door to it. So when you make your observation as a scientist, you have to take into account to stay like 20 or 30 degrees away from the sun, depending on if it's at a minimum or a maximum. But we can observe during the day.
Anyone else have a question?
Yeah, I would like to know what frequencies and what lengths of wave they actually work, the telescopes.
That is a great question. And so we see 1 to 50 gigahertz, and I think that's about 21 centimeters to about 1 millimeter. We always use the frequency designation, not the wavelength, so I don't remember quite what the higher frequency wavelength is. And 50 gigahertz, I think, is Ka band or Q band.
Any questions online?
Got a question online. Asked, what's the sensor for a radioscope?
That is a great question. It's basically a piece of wire. So we don't use CCDs. We essentially record the voltage going through a piece of wire that excites the electrons as it moves through that piece of wire. I don't know what the sensor looks like specifically for any of the receivers because it changes depending on which receiver we're using.
Anyone else?
Questions?
No? Okay, then we'll toss it back to you, Montana.
Awesome. All right, and so now we can talk about the cute science cases or the fun science cases. So for the case of this one, this is actually a supernova remnant. It's known as the Manatee Nebula, or W50. And so it erupted about 20,000 years ago because we get supernovas with really massive stars, like more than 8 times the size of our sun. And so when they erupt, of course, you can see them across the electromagnetic spectrum. But for the case of as overtime goes on, they sort of fade. But in the case of this one, it actually emits in both X-ray and radio still as a sort of remnant. And so part of the reason why is because there's actually an X-ray binary at the center, and it's also called a microquasar. And because of the nature of that binary and the wobbly nature of the binary in jets, it's actually, as it sort of kind of exploded and released a lot of mass and stuff into the system, it caused the remnant to look really odd, or in this case, like a manatee. And if you remember, oh, haha. Okay, so if you remember earlier, I showed you this where we see the jets kind of go from diagonal to almost straight. This is actually the Manatee Nebula. This is the X-ray binary at the center of it. So the VLA only sees the cloud around it, whereas the VLBA is really good at seeing this sub-arc second structure. And so, yeah. And then, so another thing that the VLA is the VLA was actually used to discover some of the first exoplanets. One of the first is Lich, was actually discovered. I think it was actually with Arecibo, but we did follow-up detections on it. And the way that we were able to observe it was because it was orbiting a millisecond pulsar. So a pulsar is a neutron star that's sort of got a really strong magnetic field, and then it has these beams of radiation at the poles of the magnetic field, which doesn't necessarily align with its rotation axis. And so as this radiation beam sweeps towards Earth, it causes a sort of high intensity radiation in the radio portion of the spectrum. And the other thing that's really important about these is they're extremely consistent with their rotation. And so we can sort of use them as like atomic clocks sometimes in space. But then what we did is we looked at the radiation beam coming back around every so often, and there was a sort of blip in the signal. And the only possible explanation for this blip was that there was a planet getting in the way of the radiation beam as it came back towards Earth. In the case of Lich, the pulsar actually it had a period of 6.22 milliseconds, and that's over 10,000 rotations per minute. So they're insanely fast. Another one that's really famous is the Crab Nebula, or the millisecond Crab pulsar at the center of it. I don't remember the period for that one, but we study those objects because we can also use them to look for gravitational waves. So we've heard of gravitational waves from like LIGO, where gravity causes bends in the fabric of space-time when highly energetic events happen, and they cause a sort of ripple in space-time. But the other thing too is we can actually use pulsars to observe gravitational waves. So we can look at all the millisecond pulsars around us and do a sort of statistical analysis of it, and just look for changes in their period over during certain events, and see if we can detect gravitational waves through them. And there was actually a paper or an article, I think in the last couple of years, about nanograv. Nanograv actually uses a pulsar timing array because they use the millisecond pulsars as sort of clocks in space. And what they found is a sort of background radiation of gravitational waves. And so that's really cool. We can even look at our own planet. So on your right is an image of Saturn, actually. And so the VLA was used to essentially study the weather on Saturn. And so using the radio telescopes, we can look at specific parts of the atmosphere. In this case, it was ammonia. So you see the more intense or the wider parts, which has more ammonia at that point. And so what they were able to see it go from like sort of the top into the like lower down. And so they were tracing the ammonia in the megastorms, and they found that the ammonia is from the upper atmosphere and it's deposited lower down because of these megastorms. And so this allows us to look at not only something cool, but we can sort of figure out like what's going on with gas giants, how the weather, sort of weather on them, like impacts like what not only what they look like, but more things about maybe how they formed and things like that. We've also used them to look at other planets. For example, we were the ones that actually discovered ice on Mercury, on the dark side of Mercury. So the VLA antennas are only receiving, but there was a signal that was transmitted from Goldstone, California, and it was bounced off of Mercury and recorded by the VLA. And the image is on your right. And so where we see green is where the signal bounced back really well. And then as it goes to the red, it wasn't bounced back quite as well. And so with the sorry, so where the red is it wasn't, because it wasn't bouncing back as well, the only possible explanation after looking at a lot more of the images and things like that was the existence of ice. So ice on Earth actually absorbs radio signals, but in ice in very, very cold spots, such as Mercury, it actually bounces the radio waves back even better. And so they were also able to determine that it wasn't even the momentary sort of reflection off of a crater wall or anything by doing periodic observations of it. And then we also found the first Einstein ring. So Einstein rings are what you see. I think the more famous ones are in optical, which are like at the bottom right, or the Cheshire Cat one. And the idea is object that's really massive. It causes even light to bend around it, which was predicted by Einstein's theory about 50 years before 1980. And they had seen a few cases of this sort of lensing effect, but it didn't make a complete arc until 1987 with the VLA with this exposure in the top right, or exposure. And they actually saw like a complete ring. And this was helping to sort of, this was only the fourth gravitational lensing thing observed. So it was helping sort of confirm Einstein's theory 50 years prior. And then speaking of supermassive objects, we can also talk about black holes. So black holes form when an object becomes so dense that even atoms, particles, or light can escape the gravity of the object. And so they would kind of look like something in the top left, but of course, which has some of that gravitational lensing around it. But we can't really see those. But what we can kind of see is the accretion disk around black holes. So when the black holes are sort of being fed, in the case of the bottom left, we have that star losing mass and it's creating this disk around this black hole. As it heats up and gets really energetic, it emits in different parts of the electromagnetic spectrum. And using radio, we can kind of get really close to almost the edge of that black hole to kind of see what's going on. And then the other thing that's cool is in the bottom left picture is as these things fall in, they can't fall in just easily because of conservation of angular momentum. It's like when you pull the plug on a bathtub or a kitchen sink and the water kind of has to slowly fall down. That's due to conservation of angular momentum. Well, because these are so energetic, they also sometimes spit stuff back out as jets, like we saw with Hercules A. And then in this case, we have the jets being seen. Now, if we were able to observe black holes, what would they look like? Well, they would look something kind of like this. And we would have these sort of really orange or really intense sort of weird looking donut, which may ring a bell if you saw the black hole pictures, including this one at the center of our own Milky Way galaxy. So this wasn't actually taken by the VLA, but ALMA was actually part of the Event Horizon Telescope to take this picture. But the VLA sort of laid the groundwork in terms of how to conduct these observations, how to do the data reduction, how to image for almost 40 years before they were able to achieve it with the Event Horizon Telescope. And so you see this cute little orange donut, and this is the accretion disk around the black hole at the center of our own Milky Way galaxy. So not only can we make cute donut pictures, we can also sort of look at the behavior of the electrons around the black hole. So we can actually see how their magnetic field or how they rotate or things like that, which is kind of what this spiral shape is trying to show you. It's showing you how the magnetic field sort of rotates and creates this cool little spiral shape. And then, so now we have the search for extraterrestrial intelligence, or SETI. So the movie Contact, of course, has Jodie Foster listening on these headphones to these aliens with the VLA. Unfortunately, we don't listen to our radio signals. We actually use it to make cute images instead, as I've shown you. The other thing that this is a great depiction of is what we do at the VLA, because actually up until 2020, we hadn't done any search for extraterrestrial intelligence. But in 2020, the SETI Institute actually funded their own supercomputer. So we have our computer to combine the signal from the pairs of those antennas. They purchased their own called the Commensal Open Source Multimode Interferometer Cluster, or COSMIC. And what happens is our data signal is essentially like perfectly copied in two, and one of them goes to our supercomputer to make the images that the astronomer has requested or whatever. And then the other one goes to Cosmic, where they're looking for technosignatures or things like that. And I think they're in the final stages of like finalizing the design. It's a bit more because when they started in 2020, they had started purchasing equipment and like actually started the project. So I think they're getting close to it, but you can find more or information about it on their website. Another thing that we've done is the VLA Sky Survey, or VLAS. And so what this is we're basically scanning images of the sky at radio frequencies over the course of 8 years. And so as it goes from faint orange to more opaque orange, what you're seeing is the different observations over the course of that 8 years to show you that we have a really sort of depth of field for making this survey. And so that way people can go in and look for their astronomical sources in the survey and see if it changed over the course of the 8 years. Another really interesting thing about VLAS is, so it's using the B configuration, but everywhere you see the yellow or the hatched yellow, it's actually using what we call hybrid configuration. So we put the north arm in A configuration and leave the east and west in B. And we do that because it's kind of like when the sun starts setting and your shadow gets really long, we're trying to fight that really long shadow. So we put the the north arm in A configuration, and it means that we can see even further below. This way we can see about 72% of the night sky or day sky. Another thing that we're working on is, of course, the next generation VLA. As I mentioned, the VLA started working as the VLA in 1980. So that means they're going on about 45 years old, which is enough for a midlife crisis. But it's also ancient in terms of electronics and some of the receivers. And so, of course, we're looking towards the next one. So the NG VLA will be hopefully about 266 antennas. And not only will they be in the plains of St. Augustine, like the one in the bottom right and maybe left, they're going to span all over New Mexico, into Texas, Mexico, even into Colorado. And we're able to do this because we're going to get like something like 60 times the sensitivity out of all of these and make absolutely breathtaking pictures. And in fact, we actually just recently put the dish on the pedestal as of like 2 weeks ago. So it's a new project. We're hoping about in a decade we can essentially turn it on and turn down or turn off the VLA, government funding willing, of course. So yeah. Any questions?
I have a question. Does the VLA has only mostly receive signals, right? But can it also transmit signals or no?
The antennas are not actually equipped to transmit at all.
Receiving.
I'm sorry?
Thank you.
Anyone else with a question? I got a couple online ones. Let me pass those on. First one is, you might have just answered this. Can the antennas be in a configuration other than the A, B, C, and D by request of the researcher, or do they have to choose one of them?
So we can technically put the antennas in the different or the hybrid configurations, like if they're not an A, B, C, or D. But usually it's not at the request of a researcher because otherwise we'd have to constantly move the antennas. So for the most part, unless you have a really special request, we stick to the 4 A, B, C, and D configurations.
Okay. Another one is there a way to do spectral analysis of the radio signals like there is for light?
Yes, absolutely. So when we record the signal, we see it across the frequency spectrum. So it's almost like already doing spectral analysis, but we can sort of zoom in on the spectral lines as you would and get even more in depth. And you would do almost exactly the same thing as you would in optical, but with radio.
All right. Anyone else?
Yeah.
And pass the microphone back.
Thank you. When visitors come or people are seeing it, and due to infrastructure nearby, how do you minimize interference?
So when visitors come to the site, we politely request that they turn their phone and Bluetooth devices off. As far as anything beyond that, we just do the best we can. So because we have the dishes and then we combine the signal from each dish, it kind of cancels some of it out. So for example, if one antenna picks up like someone's phone, if the other antenna is far away, it may not pick up as much intensity. And so that change in intensity sort of gets canceled out when the signal is combined. But it is an ongoing problem. We try to come up with sort of flagging algorithms to sort of get rid of what we think is radio frequency interference or things like that. But for the most part, we just do what we can.
Anyone else? Okay, back to you, Montana.
No, well, that's it. That's all I have.
Thank you. Thank you. I'm louder than expected. Were there any more questions online?
Everything from online.
All right, then I guess we'll stick a fork in it
Okay.
and call it a night. So thanks for joining us, and thanks everybody for coming.